Chris.
Yes, how can I help?
It is time or not?
It's time. Yes, go ahead and
Okay.
and go ahead and start. Yes, thank you. All right, we can. It's that's good. We're prepared.
I don't hear you.
You cannot hear me?
Yeah, I hear you now. I can begin or
Yes,
not?
please begin.
All is okay?
Yes, please begin.
Okay. Good morning or good evening, everybody. I thank the organizer for their invitation. This talk is a joint work with Tango Bay Monkoro at the Faculty of Science and of Techniques of Bamako. We are concerned with analog of Schrödinger representation of the three-dimensional Heisenberg groups with entries in D, where D is a closed subring of the valuation ring of the complete value fields extension of QP. This means that we are doing representation in p-adic spaces. Right. I begin with a definition of what I mean by Heisenberg groups of, and one can define these groups for any commutative unitary algebra or even only a ring. Uh, But it is the Eisenstein group over on A of order 3 is the 3 by 3 unipotent upper triangular matrix groups with entry in A. But I see here the form of the matrix. This is the groups. As the center is isomorphic to A. And what we are what our interest is to take A to B or ZP or any closed subring of a valuation ring of a complete extension of QP. In the classical case, when you consider the Heisenberg groups over R, the Schrödinger representation are completely depends from the characters, the continuous character of the additive groups R. Here, for our ring T, we need to have characters of its additive groups. For this, this closed group, this closed ring contain ZP. But the continuous character of ZF are well known. I describe them here. If you consider K a complete value field extension of QP, the group of character of continuous character of ZP in K is corresponds bijectively to the group of principal units of lambda K. Lambda K is weight is the evaluation ring of K, and G minus 1 is the disk of center 1, the open disk of center 1 and radius 1. The description is relatively easy. It is given by the ordinary to keep the power of K, K1. The formula is here. And the thing is that such characters are, in fact, strictly differentiable functions with derivative as usual. Because I say that they are power functions. We are interested mainly when the principal units K-1 belong to the groups 1 plus EP, where EP is the disk of convergence of the p-adic exponential. And with this, we have this is given by omega, only more omega, which absolute values is strictly inferior to the p-adic radius of the exponential. With this, we obtain with this we obtain an analytic functions which depends of omega, and this formula is given by exponential omega of A is the exponential of A omega. And reverse one see that this function is an analytic function. And in fact, it is a restricted power series with coefficients in K. Now, we consider our ring G include in a lambda K, and if T is an element of T, we have that omega T is also in the disk of convergence of exponential. Then we have a character over D. Now, we first consider the case where the subring is, is compact. For instance, ZP. And in fact, any compact unitary subgroup of lambda is the valuation ring of the finite dimensional extensions of QP. And Church groups, and I define now the Heisenberg groups H3 of D, which is a profinite group. In fact, as for ZP, this group is a pro-P group. That means that is the projective limit of finite group of finite groups of finite P groups. Now, if I set consider any element of H3D which depend of the parameters A, B, C, and what S equal S of A, B, C. Then, if we consider any function of f, any function f of D in K, I can put P S omega f of T equal exponential P dt plus C f of T of A. And it is clear that P A P S omega f is a continuous function of D in K. In fact, what I have a representation, a continuous linear representation of H D of H 3D into the space of continuous function of D in K. Excuse me, I have some problem, some technical problem with my
All right.
system.
What are you trying to do?
No, you can don't do nothing because it is. I have not a real computer in my hand. It's a problem. Now I describe the representation. Now the given representation, I I shall consider the tangent operators linked with it. For this, I consider I consider the quotient operator delta AF MB MBF eta C. And if I look at to delta is the usual difference quotient. And if A tends toward 0, if I have a continuous function, this does not necessarily exist. But such a limit exists for strictly differentiable function. And we obtain that, by the way, the tangent operator not defined everywhere. For MBF, this function is smooth. And I have the uniform limit, which is the omega t ft. And for the free, this only give the multiplication by omega. Now, the result is, but if I assume that T is a compact unitary subring of evaluation of the valuation rate of K, consider omega a non-zero element of EP, then the continuous linear representation H3D pi omega CDK is topologically irreducible. That means that any closed invariant subset of C of dk by p omega is or the null spaces or the wall spaces C, D, K. Well, to prove, I don't give the proof of the theorem, of this theorem, but it is not, I shall do some comments. This theorem is what I mean by an analog of the classical Schrödinger representation. The character exponential omega is a character of D, of the additive group of T, which correspond to the character on the additive group of R. And this is the continuous analog of the Schrödinger, the classical Schrödinger representation. And it is irreducible. Here to prove it, naturally, we have not at your disposition no integration. No, this is not an CDK is a continuous function. But what CDK is a complete algebra with usual multiplication and the, the subnorm. With this, what uh, we first see that if we one see that if I have an invariant subset is necessary and a closed invariant subset is necessary and an ideal. And if I can prove that there is the constant is a non-zero constant in this ideal, that I have that this ideal is equal to the space, to the whole space. Well, now, if I give if I have two number, two elements, omega 1 and omega 2 in EP, then such their correspondent representational equivalent if and only if omega 1 is equal omega 2. And also, I have a sure lemma. Now some comments. I have speak about the space of strictly differentiable function of D in K. What is the meaning? I don't give a definition. But this means that the difference, the quotient, the usual quotient, converge uniformly. And the result of this convergence is a continuous function. And this is a subset of a space of continuous function. And it is invariant by p pi omega. But naturally, it is not a closed subset. But C1dk have its own norm. With this norm, one can prove that this representation, the restriction of a representation, is also topologically irreducible. Now, as a special case of continuous function is the analytic function of K of D in K. This is also this is a non-closed subspaces invariant by P omega. We will be concerned with Chet representation in the shaker. Now, I shall do some comments when D equal ZP. give the description of all the continuous character of ZP in K to any character one can associate a continuous linear representation of H3ZP in the space of continuous function by the formula given above. Unless K1 is a, a P power new root of a unity, what is said for the above representation associated to analytic character remain true. Now, if K of 1 is a root of unity, then the subspace of locally constant function invariant by the subgroup P new ZP is invariant by K by PK. And the global spaces of continuous function of ZP in K is not irreducible, but the subspace is irreducible of finite dimension. The one parameter subgroups associated to the representation are in fact to any parameter one has three parameters and in the Heisenberg group two. And for if I take two of the parameters to p equal 1, I obtain subgroups of the Heisenberg group. Then, by the way, I obtain the one parameter subgroup which is linked to the representation by omega. The first is naturally to take the translation which is not here a parameter which is not smooth. The second is to multiply by exponential omega t, omega b, with this one parameter group is, as usual, given by exponential here, given here. where and the first one parameter group is given by the smooth character. Now I go to I go I shall speak now for the analytic representation. In this section, we consider a non-necessary compact closed unitary subring D of the group of variation of the ring of variation of a complete value field. And we have said above that we have analytic functions of D in K, and if exponential omega is an analytic character, we define linear representation of Heisenberg groups by the same formula as above. The thing here that I don't need to suppose that the ring D is compact, nothing said. It suffices to take a closed subring of a variation ring of K. But such analytic functions in a closed ring, in fact, correspond to the element of the state algebra. That is, the formal power series in one variable shows that the coefficients tend to 0. And we consider on it the Gauss norm, which in general is different if I consider such a series as analytic function on a disk. If in the unit closed disk is if the valuation of K is discrete, the uniform norm and the Gauss norm are distinct. But with the Gauss norm, I have a complete algebra. And I consider this algebra. With this, I shall do the representation. The first thing is to define if I have alpha and beta and a restrictive series, I have to define to prove that f of alpha z plus beta is a Tate series. By the way, I am conduct to introduce the substitution of series in Tate series. For this, I remember the formal power expansion, which I read as this. Fx, Fx, and y is equal this series with Fg of x corresponds to the derivative of the series over the factorial, the factorial. The first f1 is the formal derivative of the series. If now, if I consider an element of a Tate algebra, and if I take a power series, an element of a Tate algebra, such that this norm is not greater than 1, then I can do the substitution of H. I can do the substitution of H in F. Well, the formula is here. The substitutions of H in F is given by the left series. And the series is convergent in the norm of Gauss, on the Gauss norm. And at the final, I have the following. What I need really is to take the polynomial of a degree of 1 degree and coefficients in the variation ring. But this is what we need to define our representation. That's given here. Now, all things are defined. If I have an element of my an element S of my elements of if I have an S, an element of my Heisenberg groups in entries in D, then I have a representation of the Heisenberg groups are H3 of D in the Tate algebra. The formula is here because I can do the substitution. Now, once with the standard verification, one see that U, the representation defined as thus, is this formula gives representations of the H3D in the Tate algebra. And this, again, here, a remark, here I don't use any, I don't consider the Tate algebra, the element of the recited as functions. I consider them as only formal series whose coefficients tend to 0. Now, the linear representation as that I defined is continuous. The thing here, the thing more pleasant than for the continuous function because the representation here is smooth. I consider as above the quotient, and here I have a limit. The first limit exists and give the derivation of the functions. And this is a continuous operator of the delta algebra with norm 1. The second is give the multiplication, the operator of multiplication by z. And this operator is isometric. The third is not really important for us here. Now, again, if omega is not zero, the representation of H3D U omega K of Z is topologically irreducible. Here, it is the same problem. K of Z is a banal algebra with a multiplicative norm. It is a very nice commutative banal algebra. Now, what as above, any closed success is the invariant by U omega is an ideal, and by use of a Weierstrass preparation theorem 1C and using the operator of derivation, one conclude that one belongs to this idiot, and then there are proper closed invariant subsets. Now, some comments. Also, one has a sure lemma. This is not surprising. No, I shall begin to finish my talk by giving the completions of a Weyl algebra. The Weyl algebra, I have defined, I have seen that the derivation is a continuous operator of the Tate algebra. the multiplication by z is also continuous and here isometric. And we are naturally Heisenberg commutative relation. Or I skip some comments, which is not necessary for our well algebra. Now, the well algebra, I have said that D is an operator, a continuous operator on key of Z, and MZ also, MZ also. And reverse, one define the one-dimensional wild algebra A1 of K to be generated by partial and MZ. And any element can be right. Uh, the thing here that my field is of character 0. The character of the characteristic of my fields is 0. It is important as a notation. And then any element can be right. Any element of the wild, the one-dimensional wild algebra can be right in this as in a very simple manner. Well, I define the the phantom derivative, the J phantom derivative, which is the power of the partial of a derivative over the factorial. And with this, I have what is called an exponential sequences. The thing here that mz power I delta G is an orthonormal family of A of A1 of K for the norm of bounded linear operators. And if you want have just a thing, what we have, what will happen is that one has an easy description of the complete one has
So I just wanted to mark the time. It is 11:52. Just so if you want to, quickly finish up so we can get a few questions.
That I conclude that the complete White's algebra is a simple Noetherian algebra. What I was wait for a moment. I only give you the final formula. Allah, my system is disastrous. Disastrous. Well, the complete well algebra is a simple left Noethner ring with center K. And I conclude here my conference and thank you. And excuse me because my device don't work well. I finish. Chris, if you are here. You are here. Nobody.
Yeah, let's thank the speaker for a very interesting talk. In spite of the technological difficulties, I think that was very interesting, especially with this final theorem. Any any questions or comments for the speaker?
Yes.